Afternoon session. We'll have two talks. The first talk will be by Shi Li. He'll be talking about scheduling problems.
Okay, thank you, David. Thank you all for coming here. So I'm going to talk about improved approximation algorithms for non-preemptive scheduling problems using time-indexed LP relaxations. So we are going to focus on a bunch of problems, and here is a common setup for all those problems. So we are given a set J of jobs and a set M of machines, and each job J has a weight. And our objective is to minimize the sum of weighted combination time over all jobs J. So that is sum J over J, sum J in J, Wj times Cj, where Cj is the completion time of J. So you can think of a job as one interval on a machine in a solution, and the completion time of that job is the right endpoint of the interval. So for this schedule, this red job has completion time 4, and this orange job has completion time 6, and this black job has completion time 11. And our goal is to minimize the sum. And before we talk about the specific problems we are trying to solve, let me introduce a very convenient notation introduced by Graham et al. And it's called alpha, beta, gamma notation for scheduling problems. So alpha basically denotes the machine model. So we can have alpha equals P. So for identical machines, so in this model, all the machines are identical. So for each job J, you have a size Pj, and the processing time of J of machine I is just Pj. And we also have unrelated machine model. Here, for every job J and every machine I, you have a Pij. That's the processing time of job J on machine I. So this matrix P can be arbitrary. And in between, we also have a Q. So it's called a related machine. And in this model, every job has a size, every machine has a speed. So the processing time of job J on machine I is just Pj divided by Si, size divided by speed. And so beta will denote additional constraints we have for all those problems. So in this talk, we are going to focus on 3 constraints. One is Rj, so that says that a job J may have an arrival time Rj, so you cannot process this job before its arrival time. And we may also have precedence constraints. So we require J to precede J prime. That means J prime can only start after J completes. So those 2 constraints will make the problem harder, but the third one will make the problem easier. So it says all jobs are identical. So without loss of generality, we can assume all jobs have size 1. And the gamma will denote the objective function we are trying to optimize. And in this talk, we are only going to focus on the weighted completion time. Okay, so here are our results. And first, consider the identical machine model. So if you don't have precedence constraints, then you can basically get a p-task. So that's easy. So we will have precedence constraints for identical machine model. So for the basic problem, we get a 2 plus 2 norm 2 approximation, which improves the previous 4 approximation due to Munier et al. And for the special case where all jobs are identical, the same paper gave a 3 approximation, and we improved it to 1 plus root 2. And if machine model is a related machine model, then Chudak and Shimois gave an order of log m approximation, where m is the number of machines, and we improved this slightly by a log m factor. So then we consider the unrelated machine model. So in the problem of minimizing the weighted completion time in the unrelated machine model, the breakthrough result of Bansos, Srinivas, and Svensson gave a 1.5 minus epsilon approximation, improving the previous 1.5 approximation algorithms. But that epsilon is tiny, and we also get a 1.5 minus some epsilon approximation. And this is also tiny, but one technical improvement is that our algorithm is based on a very natural LP relaxation for the problem, and which I'm going to define soon. So when jobs have arrival times, and the previous based approximation ratio is 2, and we improved it to 1.8786. And those results are based on 2 papers, one joint work with Sanjin Im and one by myself. Okay, so in this talk I'm going to only focus on those 2 results, and the scheduling on identical machines with precedence constraints, and the scheduling on unrelated machines when jobs have arrival times. And the major theme of all the results we have is the use of time-indexed LP relaxations. So those are really natural LP relaxations for those problems, but surprisingly they are not considered before explicitly in the literature. I think partly because of 2 reasons. One is all those previous results, they don't need these stronger LPs, so the results can be obtained using some weaker LP relaxations. And the second, in practice, if you have those time-indexed variables, the LP size is going to be huge. But we use the time-indexed LP relaxations to improve all those results. So what is the general framework for this LP relaxation? Well, it's very simple. So remember, for every job J, we need to choose a machine I, and we need to choose a starting time S. So we will use Xijs to denote whether job J is scheduled on machine I with starting time S or not. So it's convenient to think of this Xijs variable is associated with a rectangle of height Xijs from S to S plus Pij. Then you can see we require that the total height of all rectangles on machine I covering one time point should be at most 1. So that means I can only have one job being processed at any time. And across different machines, for the same job, the total height should be exactly 1. And also, the completion time is just, we take all the right points of the rectangles for job J and take the average, where average is with respect to the heights of rectangles. And also we can capture the precedence constraints. So there is a stronger set of constraints for this constraint, but in this talk we will only use this, so this is sufficient. So we just require the completion time of J prime to be at least the completion time of J plus Pj prime. Okay, so this is a constraint we are going to use. Okay, now we move to the 2 results we have, and you can see once we have this time-indexed LP relaxation, and we know the previous results, and it's not hard to derive those results using the LP relaxations. So first, I'll talk about the unrelated machine scheduling when jobs have arrival times. So remember, in this problem, we have unrelated machine model. Every job J has a Pij on every machine I. So we have a arrival time Rj for each job J. And so in the LP relaxation, you can think of, we have a rectangle for each machine, and the total height of rectangles covering each time point on every machine I is at most 1, and across different machines for the same job you have a total height of 1 of rectangles. Okay, so our algorithm is actually based on the previous 2 approximation algorithm, and then identifying the loose part of the analysis and improve that by our time-indexed LP relaxation. So what is the 2 approximation algorithm using our LP? So we first solve the LP to get a set of rectangles. Then for each job J, we will independently do the following. So remember, for every job J, we have a total height 1 of rectangles, and each rectangle is indexed by machine I and starting time s. So I'm going to randomly choose 1 according to this distribution. So let ij, sj to be the index of the rectangle for job j. And then conditioned on this rectangle, I'm going to choose the offset tau j, so which is uniformly distributed between the starting point and ending point of this rectangle. So this is my tau j. And after I selected ij, sj, and tau j, I can just schedule the jobs machine by machine. So for each machine I will schedule all jobs with ij equals I on this machine I. So the schedule is as following. So I just pretend this tau j is j's arrival time. And then I do this greedy scheduling in this order. So when a job comes, I will schedule it as early as possible. So that means this job j either starts at time tau j or starts when the previous job completes. So for example, here I schedule red job here, tau j is here. The black job, I schedule it here, tau j is here. So I schedule immediately after the red job completes. And the orange job, I schedule it here. And this job, I schedule it here. So this is a greedy schedule. Question?
Are you going to say something about how you solve the time index helping relaxation?
Okay, for now, let's just assume the t is polynomially bounded. So by using a log 1 plus epsilon factor, you can reduce the number of different time points to polynomial, to linear, yes.
People did use this formulation before.
Yeah.
Not for this particular problem.
This particular problem also
Not for this particular.
1999 or something like that.
Yeah, not for this particular problem.
I
Yeah.
think for this one.
Really? Do they have improved results?
No, it's worse. The bounds are worse. But
It's 2, right?
it was no,
No,
it's
I'm
worse
saying
than
that
2.
the formulations,
This was
I
the
mean-
first constant. Was
Oh, really? I thought they use the non-preemptive version of it. It's not preemptive version, maybe.
No, it doesn't matter.
doesn't matter. Anyway.
Okay, I will check that. Okay, so this is the algorithm. And so what is the what's the analysis for the two approximation ratio? So we are going to analyze the job by job, focus on each job j. I will analyze the expected completion time of job j, and I will bound it by 2 times the fractional completion time. And so how can I do this? Well, I first fix this rectangle and the offset for job j, and I'm conditioned on those 3 parameters. So the completion time Cj will be the sum of 3 parts. So first part is actually the total length of jobs j prime that are scheduled on machine I, but scheduled before j. So that means with tau values smaller than tau j. The second part is the total length of idle times before tau j. So that will contribute to the completion time of Cj. And finally, it's just Pij, the length of j on machine I. So it's not hard to bound the first term by tau j. So you just consider the contribution of each rectangle. And each rectangle, the contribution is the total area of the rectangle or the part before tau j. So at each time, the total height is 1, so we get a tau j bound. And the second term, we can also bound it by tau j. That's the total length of idle time before tau j. Of course, it's at most tau j. So if you consider 2 pounds, then the expected Cj under this condition is at most 2 tau j plus Pij. And the expected value of tau j conditioned on Sj and Ij is this Sj plus Pij over 2. So it's a middle point. So Sj here, Sj plus Pij here, middle point. So if you replace tau j with this, you will get 2 Sj plus Pij, which is what we needed. Well, what we need. So finally, we have the answer. Okay, to improve this bound, let's just check what we can improve for the second term. So let's just assume this machine I is fully packed. So at every time, you have exactly a total height 1 of intervals. Otherwise, you can just add some dummy rectangles. So maybe this bound just by tau j is too pessimistic. that basically says that all the time points before tau j are idle. And you can see, suppose this is tau j here, the rectangles are something like this, then you hope to see many busy time slots before tau j. So if the rectangle lengths are very small, with some probability you are going to see next to this rectangle, and the tau j will be here. So you can see with reasonable probability, this you will have a reasonable length of busy slots before tau j. So that's okay. And it's not hard to see. The only bad case is this. So j is here, tau j is here, but all the rectangles are very long starting at time 0, ending time is very big compared to tau j. Then with high probability, all those rectangles, the tau value will be after tau j. So the total length will be, idle length will be tau j. Because the tau j is here, all those jobs are scheduled after j. So this is bad. And so that will give us the idea for improvement. So you can see this job j must have small length, all those job j have a big length. So what we are doing right now is I'm trying to increase the probability of j scheduled before those jobs by shifting the mass of the distribution from the left to the center. If you shift some mass from the left to the center, j will be more likely to be scheduled before those jobs. But on the other hand, I need to not increase the expected value of tau j conditioned on ij and sj. Remember, originally it's sj plus pij over 2. I still need to make this bound not increase. So it's not hard to prove that if I just have this distribution, so I cut the left side and cut the right side, I randomly choose tau j between, then it will improve this factor of 2. But to do a better bound, what we do is we parameterize this by a distribution. So we choose a theta j from some distribution, and let tau j be sj plus theta j times pij. Then we express this as the two terms here. We bound the two terms here by this form. So the sum over all rectangles are the contribution of R. Then it suffices to just bound the expected contribution of R to the integral solution divided by the area of R before tau j. So the total here over all R will be tau j. The total here over all will be the first two terms. Okay. So this will depend on theta, and we discretize this distribution theta and using LP to find the best theta. But eventually we will find a good fit for this distribution. So we will get an analytical proof for the approximation ratio without using the program. So here is what the distribution looks like. So from 0 to this point is an increasing function. So it's almost linear, but it's a quadratic with very small quadratic term. And when theta is after this is 0. So that coincides with our idea that we should shift mass from the left to the center, from right to the center. So to sum up, we have a 1.8786 approximation algorithm for unrelated machine scheduling when job have arrival times. So question for this part?
Do you know anything about lower bounds on the integrality gap?
Integrality gap, no. We don't know. So the problem is APX hard, and so it should be at least the hardness. But other than that, we did not try.
And what kind of constants come out of the APX hardness?
What?
And what absolute, what is the value?
I don't know. I think it's very small. When you say APX hard, you don't expect to be very hard. Very large is a constant. Okay.
there are no weights, but there is still preemption, what is something better known? Or, so I'm just asking if there are no weights but preemption. And
No
and
weights.
preemption. There are no weights, but there are still release times.
Release
Sorry, yeah.
times. I think, if you think about it, it may still be hard.
But Bunsen and Swenson's rounding won't.
Yeah, that's for different problems. You have weights, but you don't have arrival times.
So you're asking without release dates and without weights?
No.
With release dates?
With release dates, but non-preemptive. I don't think it's trivial. I think it's still NP hard, but I don't know what's the best ratio.
What is Scutella using the?
Okay, this is just the first part. Okay, what?
What is Scutella using the omelets program?
1.5.
1.5, yes. No. I mean, if you have arrival times 2.
Yeah, but that.
Okay, I think I need to be quick for the second part. 2 plus 2 non-to approximation for identical machine scheduling, but we have precedence constraints. So this is the difference from the previous problem. So we have identical machines, and we have precedence constraints. We may or may not have arrival times. For this, it doesn't matter, but for simplicity, we just assume we don't have arrival times. So since we are in the identical machine model, we can just remove the index I. So we just need XJAs right now. So each XJT, each XJS is just a rectangle from S to S plus Pij with height XJS. And across each time point, we have a total height of M. And for all jobs, for each job, the total height of rectangles is exactly 1. So this is the picture you should have in mind. And so first, we recover the 4 approximation due to Munir, and then we try to see what's not tight in the analysis, and we will improve it. So we solve the LP, and then for every job J, in non-decreasing order of this quantity. So Cj minus Pj over 2. So Cj is the fractional completion time of J in the LP solution. Pj is the length of job J. So we have identical machines, so there is only 1 Pj. And then we schedule this job J in a greedy manner. So we schedule J as early as possible, subject to 2 constraints. First, the machine capacity constraint. So that means at any time, the total number of intervals should not exceed M. And the second one is precedence constraints. You should start, you should respect those constraints. So for example, those jobs are scheduled. I need to schedule this red job, but I need to schedule it after this orange job. So I can only start it here. But M equals 3, I should find the first time slot where if I add this interval, the congestion remains 3. So this is the time I schedule this red job. Okay, this is the simple algorithm, and it gives you 4 approximation. So what's the analysis? So let's use T(Cj) to be the completion time of J in the integral solution. So then we break T(Cj) into 2 parts. So I is the total length of idle time slots before T(Cj). B is the busy time slots. So when I say busy, I mean all machines are busy. When I say idle, so that means at least 1 machine is idle. That's the definition. So idle time slots, I can bound it by 2 Cj. So that's known. So and busy, I can also bound it by 2 Cj. So that gives you 4 approximation. But I'm going to show this proof for busy time slots. So it's actually very straightforward. You have this picture of rectangles in mind. So what's this? What's Cj minus Pj over 2? It's the horizontal coordinate of the mass center of rectangles for J. So Cj is completion time, Cj minus Pj starting time, Cj minus Pj over 2 is the center. And consider all jobs scheduled before J. Those jobs should have center of mass before this Cj minus Pj over 2. So if we consider all those rectangles, the horizontal mass center should be before Cj minus Pj over 2. But at each time point, we have a total height of M. So you can see the total area is at most 2 times this times M. Just the center of mass is here. Every time point, you have height M. So you cannot start before time 0. So that's the total area. And by the definition of busy time slots, so this divided by M is the total length of busy slots before TL.Cj, which is at most 2 Cj. Okay, so here comes our modification of the algorithm. So what we do is we will choose the theta randomly between 0 and half, and I schedule jobs in this order. So Cj minus Pj plus theta Pj. So that's theta fraction from the beginning of the starting time for J. So again, we will try to break into 2 parts. For idle time slots, we can show the upper bound 1 over 1 minus theta times Cj. So this improves over 1 over 2. And but for busy time, we can only get 1 over theta times Cj. So if you want to take the base, the theta is half, and you will only get 4. So let's try to see why we can only get 1 over theta times Cj. So here is the simple example. We think of this job J, Pj is very small. So Cj minus 1 minus theta Pj is roughly Cj. But for all the other jobs, and roughly theta fraction of the job is before this Cj. 1 minus theta is after Cj. So this job will start at time 0 and ends here. So you can see the total length is 1 over 1 minus theta Pj. But you can see the crucial observation is that this cannot be bad for every theta. So indeed, what we will show is that even if we randomly choose theta between 0 and half, B will be at most 2 Cj instead of an integral of 1 over theta, which is infinity. So combining this, we get 2 for the busy time, but for idle time is the integral of 1 over 1 minus theta, so it's 2 norm 2. So that improves the 4 approximation. So to sum up, we have a 2 plus 2 norm 2 approximation for scheduling on identical machines with precedence constraints. So this is the algorithm. So there are a few open problems. So first, can we get a better approximation for the 2 problems we studied? So for the unrelated machine scheduling, we have APX hard. And for this identical machine scheduling with precedence constraints, we have a UGC2 hardness. And also, can we improve the unrelated machine scheduling if we don't have arrival times? Right now, we have 1.5 minus C, where C is very small. Can you get an approximation with reasonable C? Also, can you improve the related machine scheduling when jobs have precedence constraints? Currently, it's log M over log M. Okay, thank you. That's the end of the talk.
We can take a quick question.
Okay.
For the first question, for the first open problem you mentioned, if I allow preemption, what is the best constant, or is your?
Oh, that's also in our paper. Preemption, actually, the ratio is even worse. We get 1.9991. So previous result is 2.
That's the thing I don't understand, because for completion time, if there are release times, intuitively problem becomes easier than harder. So
You mean preemption with? It's because of the LP we are using.
only helping you.
No, because of the LP, it's easy for our solution, but it's also easy for the optimum. So our LP only works for the non-preemptive version. Right. If you have a preemption, you don't have rectangles.
Preemption, okay.
Other questions?
There, I think the easier problem is the completion time. The night span is already only.
Oh, sorry, yeah, but they're equivalent up to a constant factor. Yeah. There is a recent hardness result, assuming some hardness of some k-partite graph problem. You can get a super constant, but it's a very small super constant.
Okay, thank you very much.